So, getting started on the topic 3.9 notes, we're working with inverse trigonometric functions. And as with all functions, the inverse of a trigonometric function is the result of switching the input and output values of a function. So you switch the x and y values. As a result, the output value of an inverse trig function will be an angle measure. Because think about it, like on our unit circle usually, let's say, got my unit circle here, little unit circle. This first line of, like my angle here is pi over 6. And that was usually my input into a function. So for example, say I was trying to find sine of pi over 6. Well, I would just go to the y value at pi over 6, because this is my angle, and I output the y value, which would be 1/2. And now, if I was going to do the inverses, these would switch. That's what this is saying. So let's write that out. The output value of an inverse trig function is an angle measure. So it's going to output, for our cases at least, it's going to output one of the pi values on the unit circle. And just to be able to talk about these, let's look at this notation. We can represent inverse trig functions in two different ways. Sine to the -1, or arc sine. That's how you say that, arc sine, not arc sin. And that's what that says here. You would say arc sine of x. So we can either use this notation or this notation. Similar with cosine, you could say cosine to the -1 of x, or arc. Let me rewrite that. Arc cos of x. Arc sine and arc cosine. And then you got inverse tangent, which is arctan. These are the exact same thing. Okay? And really what that's doing is it allows you to solve equations when you have sine on one side or sine on another side. The inverse trig functions are, like it says it in the name, they are functions themselves, but the most useful part of them is being able to solve equations with them, I think. And one way you do this, so write the statement sine of pi over 6 equals 1/2 in an equivalent form using arc sine notation. So basically what it's saying is, well, I'm trying to get pi over 6 out of the parentheses, so I'm going to do sine to the -1 on both sides, arc sine on both sides, and these cancel out because they're inverses, and I have pi over 6 equals sine to the -1 of 1/2. But talking about arc sine notation, you could either write it the highlighted way here in green, or I could write the same thing. These are saying the exact same thing. I could say pi over 6 equals arc sine of 1/2. Either way, regardless of if I'm talking about the one highlighted in green or the one highlighted in yellow, I still say arc sine of 1/2 regardless. And because trig functions are periodic, they repeat over certain x values, we must restrict their domains to create their corresponding inverse functions. And the reason why we need to restrict the domain, so to restrict the domain, it's to make sure it passes the horizontal line test. This is a little bit of a throwback from a previous unit, horizontal line test. If you draw a horizontal line on a graph and it crosses more than once, is not a function. Okay, so I'll give you a second to write that down. You can pause the video. But really what I'm saying is, you can see here, in order to make the inverse of a function, we'll restrict the function y equals sine x to the domain pi over 2 to pi. So that's important to know, because right here what they're saying is they're going to restrict it from pi over 2 to pi, as they've highlighted here. Because let's look if I draw a horizontal line. Okay, this horizontal line here in purple. Well, if I restrict it from pi over 2 to pi, that means I can, like, the horizontal line test is going to work, right? It only crosses here at this point. But let's say we tried to, even just a little bit, right? Like even I just extended this line just partially down here, the highlighted portion. Now that's what I'm trying to make an inverse into. Well, it fails the horizontal line test now. So usually with sine, you're going to restrict it from negative pi over 2 to pi. With cosine, they do it from 0 to pi. And for tangent, you restrict it from negative pi over 2 to pi over 2. But notice, these are included. They're in brackets. So, and sine and cosine, they are included. But on tangent, they're not included in the domain. So like negative pi over 2 and pi over 2 are not included in the domain because they have vertical asymptotes at those 2 points. And really, this chart here summarizes all of this. So I would put a star beside this because this is super important. Important note, it's always important to remember and consider the domain restrictions when working with the inverse trig functions and values. So this is just something you're going to have to know to be able to work with this. So the inverse of sine, arc sine, is restricted from negative pi over 2 to pi over 2 included. And you can see arc sine and arc tan are very similar, except for arc sine and arc tan, like one being sine, includes those points of the domain. So pi over 2 is in the domain of arc sine, whereas pi over 2 is not in the domain of arc tan, and then arc cosine is from 0 to pi. So one thing that's going to be helpful for this is having a unit circle. So let me see here. Let me go ahead and pull up a unit circle on this page. Be right back. So looking here, we're looking at evaluating the following expressions, and I've got my unit circle. That's why I made a small pause in the video, brought the unit circle here. So once again, this is why knowing the unit circle like the back of your hand is super important. You can draw this out once again. Hopefully you're able to draw this easily from memory. And to evaluate these, there's kind of two steps. You got to think, one, like right domain restrictions. And then the second thing is find solution in that domain. So what do I mean by that? Well, if I go up here, I'm working with arc cosine, on part A, and I know the range is going to be from 0 to pi, 0 to pi. So I'm only looking for outputs from 0 to pi. So from 0 to pi, this top half of your unit circle. So right here, I'm going to write that's from 0 to pi, just to help myself remember, bracket that up. And then I'm looking from 0 to pi, like on this top half of the circle here, where is it negative 2 over 2? And remember, cosine is x. So cosine is x here, and that happens at 3 pi over 4. That happens at 3 pi over 4. Okay. Then B, similar idea, just what my range I can look at is different. So let's see here. For arc sine, my range is restricted from negative pi over 2 to pi over 2. Okay, we're looking from negative pi over 2 to 3 pi over 2. And really what this means, like negative pi over 2, remember, is going to be the same idea as 3 pi over 2. So you wouldn't write it that way. Like my range does not go from 3 pi over 2 to 2 pi over 2. But I can think of that to help me find it in the equation here. Because if I'm at negative pi over 2 and I add the period of the unit circle, like if I add 4 pi over 2, that'll give me 3 pi over 2. But, so I'm looking from here to here. And that kind of helps you think about it, right? This is at 3 pi over 2, and you're looking at everything in between there. So on there, I'm looking for where sine, or the y value, is negative square root of 3 over 2, and I am at 5 pi over 3. But the question is, though, is that in my domain? Or my range, sorry. Is that in my range? No. So, because 5 pi over 3 is going to be bigger than pi over 2. So we can write 5 pi over 3, but we need it between here. So we need to write it as 5 pi over 3 and subtract the period to get it in there. Okay. And another cool thing you can do here, you'll see this done a lot because that's a little bit confusing. Let's do it in blue. So say I'm going to do the same problem, sine to the negative 1, negative square root of 3 over 2. When you're solving this, there's a property of sine that lets you do this, to where if you have something in the inside of a fraction at like you have something inside the argument rather of arc sine, you can move it to the front and it'd be the same thing. So I can evaluate this as negative sine, like arc sine of square root of 3 over 2. And that's basically saying negative times that. And when I do that, then I'm going to have negative, and let's see where square root of 3 over 2 happens in the same interval. Square root of 3 over 2 happens at pi over 3. So I'm going to have negative times pi over 3, or negative pi over 3. Honestly, most of the time, if I have a negative in here, I'm going to choose to move it to the front as well. Like doing that method, I'd rather do the blue than the red. Then for C, I've got 10 to the negative 1 of pi over 3. And we're looking in the same, notice we're looking at the same point here, okay? We're looking between the same points, rather. And when I'm working with this, let's look and see what we have. I'm trying to find the square root of 3. And anytime you have the square root of 3, you're just like, that should just be a automatic way to think, how do I get this? Like, what am I looking for? I'm thinking something has to divide to this, because remember, tan is y over x, right? Tan is y over x. So what divided by what gives me the square root of 3? So if I have the square root of 3, I'm looking for square root of 3 over 2 divided by square root of 3 over 2 divided by 1/2. And I'll give you another couple that might be helpful to have. If I'm looking for 1 over the square root of 3, I'm looking for 1 over 2, so 1/2 divided by square root of 3 over 2. If I'm looking for 2, and those are the main two, actually, that you'll need to have, okay? So when I'm looking at this, I'm looking for, really, when are those going to divide out to that? So I'm looking for when y is that and x is that. And the weird thing is here, if you look, let's see, you might think you have two options. We're in the red portion here, and you might think that that could be here or here at pi over 3 or 5 pi over 3. But notice here on 5 pi over 3, I would have a negative divided by a positive, which would make it negative square root of 3. So if it was negative square root of 3, I'd be at 5 pi over 3. And I could also do the trick where I slide the negative to the front. The only one you can't do that with is cosine. The only one you can't slide the negative to the front with is cosine. So, and we can write that up here. You can slide the negative on these two, but not, oh, sorry, I thought that was sine. You can slide the negatives on tan and sine, or arctan and arcsine, but not cosine. So, long story short, where that happens at is at pi over 3. Okay, one more small section. Another example here, we have the angle theta is in standard position. The terminal ray intersects the unit circle at point P, whose coordinates are x, y. The point Q, R, and S are the result of the terminal ray being reflected over the y-axis, origin, x-axis. For each of the following expressions, determine which of the labeled points intersects the terminal ray at the given angles, okay? So, that was a lot, but we know from a previous problem that we can rewrite all of this. If that's xy, if that's xy, I can rewrite this as negative xy, just knowing what's negative in each quadrant. X, negative y. So, and we just evaluate it like we normally would. So, we're trying to find out, or trying to evaluate arc cosine of x. So remember, for cosine, we got to look up here and see what the restriction is. It's from 0 to pi. So on my unit circle here, I'm looking again from 0 to pi, the top up here. And out of the top up there, I'm looking for where it would just be x. So we're on here, we're on the top part, and where would it just be x? Well, it's saying where would I have a positive x, right? Where would I have a positive x? Well, that happens at P, because my x value is positive. Okay, you can pause this and try to do the next one if you want to. For sine, the restriction is from negative pi over 2 to pi over 2. And I'm trying to, so let's draw that. That's the right half of the circle. That's another thing you can do. This is the right side of the circle, right side of the circle. Just giving more ways to think about and remember this. So if I'm on the right side of the circle, I'm trying to think of where a negative y would be. And that happens here. So S. When is cosine negative? Well, that happens here at Q, because we're on the, for cosine, we're on the top. And Q. And then when is tangent? Remember, tangent works with the right side of the circle. So when is it negative y over negative s? Well, right here, I would have negative y over x at point S. So another way to think about cosine is top, and there's your notes.